Okay, moving into the programme. This morning we're going to start with a session on applying evolutionary approaches to public health. We thought this was appropriate given the location of the conference in a School of Public Health, but we're also catching on to the zeitgeist here as evolutionary approaches to health and more applied evolutionary approaches are becoming more prominent in the discipline. We have EHBEA members David Lawson and Mari Gibson, who are pioneering the new discipline of applied evolutionary anthropology. But the people you're going to hear this morning are actually amongst the very small handful of people who are quietly already applying evolutionary approaches to public health. The first speaker will be our second plenary of the conference, Professor Jonathan Wells. Jonathan's work is truly interdisciplinary. He started out in anthropology. His first degree was in social anthropology, postgraduate work then in biological anthropology. But his post-PhD career has been very much focused on the practical applications of evolutionary theory to nutrition and energy metabolism. And he's done pioneering and very valuable work on these topics across the globe. His website says that he currently has projects running in many countries across the globe in all continents. So he's a very busy man. Alongside that empirical work, he has also throughout maintained a strong interest in developing evolutionary theory itself, and he's written a number of very, very well-received papers trying to grapple with evolutionary theory and how we can use it to understand health-related issues. He's now Professor of Anthropology and Paediatric Nutrition at UCL's Institute of Child Health, so his title combines those two strands of his career. He's also interested, however, in incorporating the wider social context into the understanding of health. He's written, for example, on capitalism and how that affects energy metabolism. And I think his career really typifies what an academic career should be. So his publication record is extremely long. I do not recommend you look him up on Google Scholar unless you want to feel inadequate this morning. But it's also very broad, as I've already suggested. And it also really builds on what he's done before. So he does not take the hit-and-run approach to publications where the only aim is to get publications in high-impact journals. His work is much deeper than that. He really thinks very hard about what he does. His work builds on what has gone before, even to the extent of writing books, which is something that's not too popular in academia these days. But I think it typifies his very deep approach to what he does. And despite all this, he's also very generous with his time. It's thanks to him that David Lawson and I know how to measure a subscapular skin fold, which he taught us to do when we were in the Gambia in the field a few years ago. And he also has the capacity to surprise people. So on two separate occasions, people who've met him for the first time have come up to me afterwards and said, "I didn't realise he was so young." Jonathan's CV is both so long and so broad. Both of these people had assumed that he must be a very eminent professor on the verge of retirement, if not beyond it, and were really quite surprised to find that he is not on the verge of retirement by any means. I hope we have a good couple of decades more work out of Jonathan before he retires. So I'm extremely pleased to hand over now to Jonathan Wells, who is the second plenary of our conference.
Thank you very much for that kind introduction. I should explain that I also work with a huge number of wonderful colleagues in all these other countries worldwide, so that I just go and visit, and they do all the hard work running the studies. Okay, so what I want to do today is to talk about the issue of how we try and prevent chronic diseases from an evolutionary perspective. Now, non-communicable diseases refer to cardiovascular disease, type 2 diabetes, hypertension, stroke and obesity in particular, but the arguments that I'm making are relevant to a number of other diseases such as osteoporosis, Alzheimer's disease, many forms of cancer and so on. It's very simple why we need to get interested in these diseases, because they are rapidly becoming the main source of morbidity and premature mortality worldwide. Now, here we are at the European Human Behaviour and Evolution Association, and you may be thinking, why do I want to come and hear about diseases, patients, and so on? Where's the evolution, where's the behaviour in that? So my aim in this presentation is to try and tell you how important it is that we recognise the value of adopting an evolutionary approach, and also that we really think about behaviour and its role in the etiology of these diseases. If we don't understand the behaviour, we really have very little chance of preventing them. Now, chronic diseases have their onset in middle and old age, so that's when they're evident to the clinician. And by the late 20th century, two key risk factors had been recognized. One was genotype, because these diseases tend to cluster within families. And the other was an unhealthy adult lifestyle, an unhealthy diet, gaining too much weight, behaviors such as smoking, and so on. But the fact that we deteriorate in later life is nothing new. This is an effort to estimate the probability of dying in the city of Rome in 300 AD. And what you can see here is that after the age of 45 years, the probability of dying starts to accelerate. So although there are all sorts of different sources of mortality in this population, that reflects the increasing extent to which the body is literally just falling apart, and people are dying of the fact their body can't maintain itself, as well as infectious diseases. So because these diseases affect adults primarily, the main public response has been to target adults and tell them they shouldn't behave like this, where everyone is behaving extremely badly. We're supposed to take responsibility for our lifestyle. We're supposed to know how to eat healthily, we're supposed to be active, and we're supposed not to do things like smoke cigarettes. But in the last 2 or 3 decades or so, our understanding of chronic diseases has undergone a profound shift, inspired to a large extent by the work of David Barker and colleagues in Southampton. This was one of his classic papers published in 1989, when he showed us that weight in infancy was strongly predictive of the chances of dying of ischemic heart disease in adult life. There was something about development that was also important. And we now know that there are critical windows early in life during which environmental effects can shape phenotype, and those effects are going to track on into later life. It's not possible to reverse all of these effects. So we can refer to critical windows of physiological sensitivity when we're especially vulnerable to nutritional effects. So we need a life course perspective. Chronic diseases are simply not like infectious diseases. You don't get bitten by an insect and contract an infectious disease in the same way with chronic diseases. They have this life course development. We know that plasticity early in development is implicated, and we know that plasticity later in our life is also important because we can change our disease risk by the way that we behave. And these come together to shape our chronic disease risk overall. But that also means it's quite difficult to understand what we should be doing to prevent these diseases if they are shaped so early on in the life course. And it's also difficult to understand how we should interpret plasticity. If we're evolutionary biologists, we tend to assume that plasticity is somehow a good kind of thing. It allows us to fit organisms to the environment, and we like to use the word adaptation. And yet what we're seeing here is all sorts of components of plasticity lead down the path towards serious ill health. Well, that doesn't look very adaptive at all. So how do we square this paradox? And how effective is our knowledge so far in actually preventing these chronic diseases? Well, these graphs come from a paper that was published just last week. You may have heard it on the radio if you're here in the UK. This is just the number of men and women obese worldwide. And you can see that if we have knowledge, we're not doing very well in applying it to prevent the spread of the obesity epidemic. So it's an exponentially increasing situation in each sex. Equally, we're not doing that well in preventing malnutrition, undernutrition in children, the other range of the spectrum. So we have this obesity epidemic, and yet it coexists with very prevalent child malnutrition. So these refer to millions of malnourished children in different parts of the world. So we've actually got what we call a dual burden of malnutrition, which is a main public health burden worldwide. And these nutritional effects are driving drastic changes in mortality rates. So you can see that death rates over the last 20 years have decreased a little bit for some infectious diseases, such as tuberculosis or diarrheal diseases. But if you look at the bottom of the graph, then deaths from cancers, ischemic heart disease, stroke, diabetes are really increasing. And they're becoming the main source of premature mortality almost in every global region. It's not just something about high-income countries. Now, if you live in the UK, you're probably aware that we think that we're living longer lifespans. We're told that more of us are living into old age. And so that tells us something interesting. It tells us that aging is not a kind of universal scenario. We can change the rate of aging according to the circumstances in which we live. But perhaps more importantly, there's major variability in aging between different components of the population. So there are data from England between 2009 and 2011 comparing the lifespan and also the years of healthy lifespan between different social groups. And what I put here are the data for the poorest versus the wealthiest tenth of the population. You can see that the poorest men die 9 years earlier than the richest men, and for the women the difference is 7 years. But that's not all, because the difference in the duration of the healthy lifespan is different by approximately 20 years in both sexes. So the poorest segment of the population is living with chronic diseases for up to 20 years of their life. And this is a major burden on the quality of life, just as well as life expectancy. So how are we going to understand this? So what I'm going to try and do in this presentation is to explain the benefits of adopting a multidisciplinary approach. Now, some people study chronic diseases by looking at the physiology. How does the disease manifest? There are a few of us who are interested in trying to look at the evolutionary biology and understand why we have traits that allow us to develop these diseases. And there have been a few people who've been interested in the organization of society, how we behave with each other, which is relevant. But the aim of a multidisciplinary approach is that by drawing these three things together, we get more than just the sum of their parts. We actually get a bigger integrated view. So that's what I'm going to try and do. And the talk that I'm going to give is really based on a book that I've just written and which will be published in June this year, and it tries to follow this approach. What I'm interested in ultimately is the social basis of chronic disease risk. But in order to understand that, we really do need to dig into metabolism and work out why we are like we are, why evolution has shaped us to have the metabolic traits that we have. So let's start with the physiological component of this approach. So these were some of the early types of data that were published when we realized that development was important in the pathway towards chronic disease risks. And this cohort study showed that the risk of having heart disease in later life was greatly raised in those who were born with low birth weight. And this wasn't just something about heart disease, it refers to many other chronic diseases as well. So here you can see exactly the same pattern for glucose intolerance, which is failure to regulate blood sugar levels, a key risk factor for diabetes. And cohort after cohort replicated these findings. It wasn't just something strange in two British cohorts. Low birth rate has been consistently associated in many different countries worldwide with the overt risk of having these chronic diseases or indeed of dying from them, and also at younger ages with physiological markers of risk, traits like insulin resistance, blood lipid levels, arterial disease, and blood pressure. And one of the most insightful articles that David Barker was able to produce was a paper where he compared the growth rates of adults who in adult life had or did not have a coronary event. The blue line sets to 0 the growth patterns of all those who did not have a coronary event, and then the red boxes show the growth patterns of those who did. And you can see three interesting things. Those who went on to have a coronary event were born slightly small. They continued to show poorer rates of growth in the first 2 years of life. And then from 6 years of age, they started to catch up, particularly in weight, so that you can see their BMI line just starting to cross the other group. Now, to make sense of these data that were increasingly linking early growth patterns in the start of life with the risk of chronic diseases in middle or old age, Nick Hales and David Barker produced the thrifty phenotype hypothesis. And the idea here was that the fetus was responding to undernutrition by reducing investment in some organs in order to prioritize sending energy to the brain. And they identified that the pancreas and the liver might be two of the organs that were sacrificed to protect the brain. And they suggested this would be, in the short term, a survival phenotype. It's a way of coping with an inadequate energy supply by cutting your costs. The problem would come later in the life course, because going down the line, if you have a reduced pancreatic function, then you're less tolerant of nutritional excess in later life. So traits such as obesity, physical inactivity, and consuming a rich diet. And there are some very nice data that emerged early on that supported this. So here you've got birth weight quartile along the front, and you've got either adults with normal BMI or who are both tall and obese at the back, and adults with systolic blood pressure on the left-hand y-axis. You can see that if you have normal BMI, birth weight doesn't have much to say about your adult blood pressure. But if you're obese and tall, then if you were born small, then you have much greater systolic blood pressure. So this is sort of very nice evidence showing the value of the thrifty phenotype hypothesis. But what was really particularly interesting about all of these data linking birth weight with chronic disease risk, that it wasn't actually something restricted to small babies. Rather, what you're seeing is a dose-response inverse association pretty much across the whole of the birth weight range. The heavier your birth weight, the lower your risk of these diseases in adult life. And again, that's not something just for heart disease. See exactly the same thing for other diseases, so the same data here for glucose intolerance and diabetes risk. Now, most of the association between birth weight and chronic disease risk lies within the normal birth weight range. So it's very difficult for us to start discussing malnutrition, undernutrition, if the babies are being born with typical birth weights. Rather, what we're seeing is that every additional unit of birth weight reduces chronic disease risk. It's just better to be bigger when you're born. And in fact, we may not need to focus so much on nutrition itself, because what we're seeing here is a growth trait and its association. So perhaps we should look in more detail at growth. Now, if we do look at growth, then it can be divided up into two different basic periods. The first is hyperplasia, and the second is hypertrophy. And hyperplasia is the period during which growth is mainly about the increase in cell number, and hypertrophy is the period when growth is mainly about the increase in cell size. And building on the thrifty phenotype hypothesis, which I found extremely stimulating, I suggested that we could define two generic traits which tend to develop largely in these two different periods. And the first I've called metabolic capacity, and the second I've called metabolic load. Now, metabolic capacity refers to characteristics of organ structure and function, and they confer homeostatic capacity, and that's important right through the life course. These are the organs that keep the body in good condition. They essentially prevent wear and tear. They stop the aging that you're seeing there in the population from ancient Rome. And because they develop during the period of hyperplasia, they are strongly contingent on the magnitude of early growth, both fetal growth and infant growth, although individual traits vary according to which is more important. And I just want to show you a few examples of how organ traits, structure and function correlate in a dose-response linear manner with birth weight. These are data from Ethiopia. It's a cohort where we've been measuring lean mass and fat mass with the PPOD, and you can see here that birth weight scales very tightly with lean mass at birth in this population. These are data on the capacity to secrete insulin at 8 years in the Ausbach cohort according to thinness at birth. So it's a little different from birth weight. This is weight adjusted for length. But again, size at birth has a dose-response association with the capacity to produce insulin, which of course is essential for maintaining blood glucose regulation. And this is the number of nephrons in the kidney, and the nephron number is very important for maintaining blood pressure, and nephrogenesis ceases at birth. You can't get more nephrons in postnatal life. So once again, the heavier you are at birth, the more nephrons, the more you're going to be able to regulate your blood pressure. Now, what challenges homeostasis is a number of different factors. Many of you will be familiar with the concept of allostatic load, and that refers to the stress response on the EHBEA axis, and in particular, the hormone cortisol, so that we know that through the stress response we can challenge homeostasis. But what I'm interested in is the things that pertain more generally to nutrition as we generally think of it, and I've called it metabolic load. It's particularly concerned with fuel homeostasis and other components of homeostasis that go closely with that. So we're looking at basic energy metabolism. And the hormone that perhaps is of most interest is insulin, but then there are a number of other hormones that are also important for basic homeostasis. And the idea is that there are a variety of components of metabolic load, each of which can challenge homeostasis. We can think of a lipogenic diet, a fattening diet, smoking, which perturbs blood lipid concentrations as well as arterial health, obesity, sedentary behavior, also infectious diseases because they have big effects on our metabolism when we're sick, and of course psychosocial stress, so there is a little bit of overlap with allostatic stress as well. And these loads can induce signaling perturbations or fuel homeostasis perturbations or hemodynamic perturbations, high blood pressure. And all of these, therefore, challenge the body's ability to maintain homeostasis. And if you can't maintain homeostasis, then the body is going to show more and more wear and tear. Now, exactly what it is about metabolic load that damages our health is still a work in progress. You'll mostly be familiar, I'm sure, with the debate, is it fat that's bad for our dietary health, or is it refined carbohydrate? In the field of physical activity, is it that it's good to run around and be active, or is it just that it's bad to sit around and be sedentary? And when we look at obesity, is it that we're too heavy, or is it that we've got too much fat or central fat, or is it the underlying metabolism which is doing unhealthy things to specific organs and tissues? So this is an ongoing area of work, but I still think that we can use these concepts. So this is the capacity load model of chronic disease risk. So along the front we have groups of metabolic capacity, which we could most simply measure just by birth weight, but we could be more specific and collect some data more related to specific organs or tissues. Up the right-hand side, we have tertiles of metabolic load. Again, most simply, childhood BMI, adult BMI, childhood weight gain, or so on. Or we could look at body fat content, dietary intake, and physical inactivity. These are all components of load. And then up the left-hand y-axis, we've got the risk of all the diseases: diabetes, heart disease, stroke, and hypertension. And the idea is that we should see dose-response associations interrelating these two risk factors in relation to chronic disease risk. So, whatever your metabolic load, the idea is that if you have less metabolic capacity, you'll have a greater risk of these diseases. Equally, if you have any amount of metabolic capacity, if you increase the metabolic load in later life, again, you will increase chronic disease risk. And that means that we should expect the highest risk of chronic diseases in those who are born small with low capacity and go on to acquire a large load, obesity and other related things, so they've got the highest risk. And if you remember, that's exactly what the growth patterns were showing in the study of David Barker. The people who had the coronary events were small in early life, but they had this catch-up weight gain from 6 years of age. Okay, so that's a model. How good is it at actually fitting with the data? It's surprisingly good at actually explaining the data that we see. These are data from 3 US cohorts published last year. And you can see a number of unhealthy lifestyle factors on the right-hand side, but there are things like smoking, high BMI, an unhealthy diet, and being inactive, and so on. And so people were just grouped according to how many of those they had. And we have birth weight on the x-axis and the risk of diabetes as the outcome. Now again, you can see that if you have a healthy adult lifestyle, it doesn't really matter very much what your birth weight is. You have a very low risk of having diabetes. Whereas at the back of the graph, if you're leading an unhealthy adult lifestyle, then you can see that you have an escalating risk of diabetes if your birth weight gets smaller. And again, it's not just about one chronic disease. You see exactly the same pattern for hypertension. This is the same cohorts. Once again, for those who are healthy, birth weight doesn't really generate a lot of risk, but for those who are leading an unhealthy adult lifestyle, the risk increases inversely with birth weight. Now, I've focused so far on birth weight as the sort of primary risk factor for low metabolic capacity, and talked about metabolic load quite generally. But we can actually identify a number of different traits which are strongly associated with chronic disease risk. So here on the right-hand side we have childhood BMI. And because children do differ in their birth weight, I shouldn't say kilograms, I should say I think there's a ponderal index unit on the front. You can see that childhood BMI, which is essentially a marker of catch-up growth between birth and childhood, also strongly shapes chronic disease risk, in this case mortality from coronary heart disease in old age. So catch-up growth is an important risk factor. Then the timing of menarche is also predictive of these chronic diseases. So this is the odds ratio of diabetes, and you can see on the left the unadjusted data. So clearly those with early menarche have an elevated risk, and there's some indication that perhaps those with late menarche also do. Even if you adjust for body fat, and we know that body fat is itself a chronic disease risk factor, you can still see some of this association remaining. So the timing of pubertal development also shapes chronic disease risk. And then there's adult stature. Now these are data on the risk of type 2 diabetes associated with tall stature. And you can see that all the odds ratios are, in most cases, below 1. So tall stature is protective. And we now know that generally short stature is associated with an increased risk of chronic diseases, although the data don't always support that hypothesis. And finally, the one that we know most about, adult obesity. So this is the odds ratio of the metabolic syndrome. And you can see that as you push through overweight into obesity, then the risk of developing the metabolic syndrome increases exponentially. So there are these different components of metabolic loads that we could pick out. While we're sticking with physiology, there's one other important thing to notice, which is that both capacity and load track very strongly with markers of social rank or socioeconomic status. These are data from Brazil, and we have family income in the number of minimum wages on the x-axis, and then there we have the data for birth weight and weight gain in the first 12 months of postnatal life. And you can see that the wealthier families produce babies who are heavier at birth, and they also tend to have higher rates of weight gain after birth. So social rank is clearly having a big impact on metabolic capacity. But if we look in childhood, we see the slope going in the opposite direction. These are data from the UK, the level of deprivation and the prevalence of obesity in school children in different years. And you can see an inverse association. The wealthier you are, the lower the level of obesity in that particular part of the population. So again, a strong association between metabolic load and socioeconomic status. But why do these traits predict chronic disease risk? Birth weight, childhood weight gain, age at puberty, adult height and adult BMI. We need to understand why this package of traits is doing particularly well at explaining from a broader perspective the life course pathway to chronic disease risk. So to understand that, we need to move on to an evolutionary perspective. So, during the 20th century, much of the interest in human evolution was directed to understanding the traits that all humans have. Also, the things that were very evident in the fossil record. So, bipedal locomotion, interesting hands with opposable thumbs, and of course, the large brain. And if people got interested in metabolism, it was generally to address questions that were associated with those traits. Is bipedal locomotion more efficient energetically than quadrupedal locomotion? Do we get some payoff for walking upright? How do we manage to afford for our large brains, which have a very high glucose requirement? And what did things like using tools and being social mean for our energy budgeting? And these traits, upright locomotion, large brains and so on, were generally assumed to be some kind of solution to ecological stresses that had acted on ancestral hominins, although it's been quite difficult to actually say what the real benefits were of these traits. Perhaps there was climatic stresses, perhaps it was something about the spread of the savanna ecosystem, or perhaps humans were becoming more social and generating some of their own selective pressures. Certainly, if we look back in the record of paleoclimate, we can see that there were some strong signals of environmental change. So these are data from the last 5 million years or so, and these are delta isotopic units, but they relate to temperature, the mean average global temperature. And you can see that during the period of Homo evolution, the world did indeed get cooler. We also know that during this period, the savanna ecosystem spread across Africa, and that's where humans evolved. And so there's been much interest in what's become known as the savanna hypothesis, the idea that the traits that hominins and early humans had were the ones that worked well in this particular kind of environment. And the underlying pathway for adaptation would be just genetic change through natural selection, giving a phenotype that was going to do better in these circumstances. But we see something rather strange if we look at recent human evolution. So over the last 200,000 years or so, humans have left Africa and we've managed to colonize all the major land masses of the world. And yet when we look at how we've done this, we haven't really done it through genetic adaptation. So these little trees at the top here are some kind of graphical indication of the magnitude of genetic variability in a species. And all you need to notice that the red tree at the top for humans is smaller in magnitude than the yellow and the green trees underneath for chimpanzees. So humans, despite going to all these different environments, have a lot less genetic variability than chimpanzees, who are actually occupying a narrower range of environments. So we can call ourselves the ape that won't commit. We don't actually go to these different environments and adapt to them through genetic change. Something else is going on. I've been very influenced by the work of Rick Potts, who wrote a number of articles towards the end of the 1990s suggesting that the real ecological stress that hominins faced wasn't anything specific. It wasn't the savannah, it wasn't hunting. It was actually the fact that the environment was getting more and more volatile. There was more and more ecological change. So what he pointed out on these climate record signals, was that the magnitude of the oscillations was getting larger and larger during the period of hominin evolution. Okay, so these are global annual temperature data. What does that mean at a more local scenario and over shorter time scales? Well, he suggested that even during the lifespan of individual hominins, there would be substantial ecological change both within seasons and across seasons and so on. And this was the real stress that hominins had to solve if they were to remain viable in the savannah. Now, in volatile environments, it's less about adapting by committing to one specific trait through genetic change, and more about learning, in an evolutionary sense, how to manage a basket of ever-changing risks. What we needed to evolve was the capacity to be plastic and to respond to stresses during the life course. And many of those stresses could be buffered through different forms of physiological or behavioral flexibility. So that can take us into life history theory, because now we can get back to metabolism and think how we actually, through our metabolism as well as our behavior, can respond to ecological signals. Now, life history theory, as I'm sure most people here know, involves a set of decisions, obviously not conscious decisions, about how fast an animal should live, how long it should keep growing for, when it should stop growing and start reproducing, and how many offspring it should produce and how large each offspring should be, how much to invest in them. And much of the early work on life history theory focused on explaining differences between species. So we know that there's a fast, slow continuum. A species like a mouse doesn't expect to survive beyond 1 year of age, and its physiology and its reproductive behavior is tailored to that scenario. And then we have other organisms that can live for 60 times as long, and clearly their biology is very different because of that. And these species differences in lifespan are orchestrated by differences in the way that energy is allocated between competing functions. The classic functions are maintenance, growth, reproduction, and immune function. Of course, we're very interested in maintenance because it's through maintaining the body that we hold back the diseases of wear and tear. We can see how the risk of dying shapes the optimum maintenance level and therefore the lifespan of the organism. So on the left-hand graph here, you can see that as you move to the left, as extrinsic mortality risk declines, then it makes sense to invest more energy in maintenance, because if you're not likely to die, then you need the body still to be working so that you can capitalize on that. If you do invest more in maintenance, then if mortality doesn't strike, you should see that the lifespan increases. So we see a positive correlation between maintenance level and lifespan. But we can also apply life history theory not just to consider differences across species, but we can also see how it refers to our plasticity within the life course. And suddenly this gives a new perspective on the traits that I mentioned earlier. Birth weight, childhood weight gain, age at puberty, adult size and BMI. These are all traits that emerge in part through differential investment of energy. That's why we see differences between individual humans. And these are tailoring some trade-offs to ongoing ecological cues. And we've seen that they have profound implications for the rate of aging. Now, what do other species do in volatile environments? I don't have time to go into this in detail now, but I wrote a paper a couple of years ago when I tried to use El Niño as a model of ecological volatility and look at how other animals had responded to this and see if humans were following the same pattern. Other animals that are exposed to volatile environments show a large degree of phenotypic flexibility, plasticity in growth, so they grow fast when conditions are good, but they can slow growth when it's bad. Reproductive flexibility, the opportunity to accelerate reproduction in good periods and shut it down in bad periods, and the use of social cooperation to benefit from more resources. And we see many of these same traits in humans. Each of the large brain, our slow overall growth pattern, our substantial plasticity in growth and maturation, our body fat, our cooperative breeding and our stacking of offspring, which is like a reproductive conveyor belt, they all look like traits that would be very useful to have if you were an organism exposed to volatile environments. So that we can see that we have a chain of reaction norms through which we continually can be plastic and we can respond to environmental circumstances because they are going to change through the life course. The conditions you're born in are not going to be the ones that hold throughout your life course. I'd like to focus just on one of these traits with a few slides. We know that obesity is perhaps the strongest ecological trait in humans that's tracking the chronic disease epidemic. So we need to be interested in why we actually are able to become obese. Now, while all the attention is directed to the penalties for having too much fat, we need also to remember the benefits that we get from being able to have fat in the first place. These are data on what happens during a period of severe starvation, the changes in the mass of different organs. You can see that by far the greatest change occurs in adipose tissue at the top. And if you like, that soaks up the stress of starvation, and the other organs therefore change to a smaller degree. And what you're preserving through your use of body fat is the organs that maintain homeostasis. So fat is buffering the more important parts of the body. So that's during a bad time, but during a good time, you can go and get that fat back. So these are data on a wonderful study by Patrick Pasquet and colleagues who studied the Guru Wala ceremony in a population from Cameroon. This is a ritual ceremony during which people deliberately overeat for about 3 months. And as you can see, compared to baseline during the ceremony, they literally double their energy intake, but they keep the same energy expenditure. And over this 3 month period, they gain, on average, about 15 kilograms of weight, of which about 11 or 12 kilograms of fat. So this shows that although we can use fat to buffer stresses, we can also gain fat very readily. We have a metabolism that permits that. But we probably didn't experience outright famine as the main stress during evolution. There would have been other more subtle stresses when energy intake was not exactly matched to energy expenditure. These are data on weight in female farmers from the Gambia. Year on year, these farmers are exposed to a hungry season and a harvest season, and you can see that weight rises and falls with this annual cycle. And it changes between 3 and 4 kilograms in most years. And most of this weight change is attributable to fat. So the women lose fat during the tough period and they gain it back again during the plentiful period. So that just shows you how useful fat is, and it's plastic. And now perhaps we can understand why we're so good at responding to the obesogenic niche. Now, what's really important about these traits is that they're very helpful for accommodating both the tough times and doing well during the good times. Because the challenge of a volatile environment is it's no good surviving the tough time if you don't get out and breed during the good time. So growth is flexible. It can slow during the tough times, but it can accelerate, and we can have earlier maturation during the good times. Fat is very good for giving us energy when we can't obtain it from the diet, but it's also very helpful for funding rapid growth or rapid reproduction. It can also fund immune function. We have flexible reproductive physiology so that it can shut down and open back up and accelerate depending on ecological conditions. And the brain plays a key role in different ways. So we can store information in the brain about where to find fallback foods during tough periods. And the brain is also instrumental to our ability to breed cooperatively, which helps both protect reproduction during tough times and also produce more children in the good times. Okay, but what actually shapes variability across individuals in the pace of life history? Now, up until now, most attention has been directed to extrinsic mortality risks, the infection, disease burden, psychosocial stress and trauma and so on. And there's quite a large body of evidence showing that in environments with high sources of these risk, then it makes sense to have a faster life history strategy. But I want to focus instead on what is happening in utero, which is the time when we're building the ability to maintain the body. Now, there's another theory about why plasticity in early life is linked with chronic diseases, and that is the predictive adaptive response hypothesis of Gluckman and Hansen. And they've suggested that organisms try during fetal life to gain information about the quality of the environment and use it to predict the adult environment that they're likely to breed in a few decades' time, and they try and match their phenotype in anticipation of that adult environment. So if they do match, then they should have good metabolic health, but if they can't make the match, then they would have ill health. But there are some problems with this approach, and if we go back to the idea that humans have plasticity and we buffer ecological stresses, one of the most noticeable things about pregnancy is the ability of the mother to buffer the growing fetus from external fluctuations in energy intake and energy expenditure. So what the fetus is actually exposed to are traits like maternal height and uterine volume and energy stores in body fat, and also her homeostasis, her blood pressure, glycemic control, lipid levels, and so on. So building on the embodied capital theory of Kaplan and colleagues, what I suggested that what really shapes the experience of the human fetus and during fetal life is a number of different dimensions of maternal capital. So we might think of cognitive capital, reflecting the knowledge and education that a mother has, or different types of somatic capital. And the fetus is also exposed to the reproductive scheduling of the mother. What offspring has she produced previously, and how is she caring from them? And I've also suggested that the duration of critical windows has evolved to match the duration of maternal care. The development of metabolic capacity, as we have seen, has lifelong implications for preventing aging, and therefore it's important to protect it from environmental perturbations. And that protection can be gained by occupying the physiological niche of the mother, who provides the homeostasis to smooth over all the different signals. So my model of plasticity as adaptation is rather different from Gluckman and Hansen's. I assume that if the offspring is making any adaptive response, it's to the phenotype of the mother, because that's the only source of environmental variation that is actually able to detect. And we can certainly see strong imprints of maternal capital on offspring development in early life. These are data from India, so we have maternal height on the x-axis and two types of undernutrition and mortality risk on the y-axis. And you can see that shorter mothers produce offspring that are more likely to be stunted and overweight. And of course, that's still the development of their metabolic capacity. So this is not good for their lifelong health. What's interesting about this component of capital is that the mother's height is also sensitive to the conditions that she experienced during her own development. So this is a long-term transmission of capital from mother to the offspring. But we can look beyond the body. These are data just published on the association across countries in the magnitude of gender inequality and child growth outcomes and mortality rate. And even if you hold constant for gross domestic product, what this analysis showed was that women living in less gender equal societies were more likely to have children with low birth weight, stunting and wasting. So again, the status of women in society is affecting the metabolic capacity development in the offspring. Now, we saw that there are these series of life history decisions, and that these are how the individual organism responds to the environment as it grows, and they have implications for aging rate ultimately. But obviously, each decision can only be made in the context of the decisions that were made previously. And if we follow all these decisions back, then we arrive at the first decision, how large to be at birth, and we know that that is very strongly imprinted by maternal capital. So let's think a little more about the significance of investment during critical windows. We know that metabolic capacity isn't just something that's relevant to the short term. It promotes lifelong maintenance. It's giving the organs that will slow the rate of aging by preventing wear and tear. This means that if you acquire less capacity for maintenance in early life, you're likely to age faster, and that predicts a shorter lifespan. Now, that means that you are, from an evolutionary point, it would be better for you to grow up sooner and start breeding earlier, so that you can produce some genetic fitness before you die. Now, if you get more energy later in the life course, it's too late for it to benefit metabolic capacity, so there's only other life history functions to which you can direct the energy, such as reproduction. And so that leads to a kind of conceptual approach like this, where we can see an association between the magnitude of maternal investment in early life and the pace of life history that the offspring should adopt. Now, I'm going to talk in a minute about some data from a South Asian population living in London, and this is not the only association that we might see, it's just one example. But what we can do is test whether life history pace is indeed associated with the magnitude of maternal investment. Less investment predicts a faster pace of life history, suggests less investment in growing tall, more investment in acquiring energy for reproduction, and that would have some costs in metabolic health. And you can see all of these predictions are supported in this study of South Asian women. More maternal investment, proxied by a higher birth weight, is associated with a later age at menarche, so more investment slows the rate of maturation. For those who had a higher age at menarche, they also went on to become taller in adult life, presumably because they could grow for longer. Conversely, those who had early menarche tended to have higher body fatness at the start of adult life. And finally, you can see that if you had higher body fatness, you had a higher blood pressure. Although I should stress that none of these individuals in their 20s were anything close to the cutoff for hypertension. So here you really can see how there's a chain of events going through the life course in which the level of maternal investment at the start is associated with various life history traits subsequently. So we can think of this as another trade-off during which the offspring benefits from getting protection during the most vulnerable period of its life when it's trying to develop its metabolic capacity. It gets that protection, but at a cost of bearing a lifelong imprint of the magnitude of maternal capital. If your mother didn't have much to invest, you're going to track through your life reflecting that. And so that has life history consequences from that point on, including the rate of aging and hence the risk of chronic diseases. Okay, so we've seen that maternal capital may be very important for shaping the chronic disease risk of the offspring. But why do mothers differ amongst themselves in the magnitude of maternal capital? So we could think about ecological factors, climate, the dietary energy supply, micronutrients, the burden of infectious disease. We could also think about the reproductive strategy, how many offspring are being produced and when does reproduction start. But I want now to shift to social rank, which I think is a particularly important component of social maternal capital. So now we move on to the society component. Now, when we get to looking at humans from a societal perspective, we can add something extra into our understanding of life history strategy. The best strategy for you may depend on what others are doing in the population. And that takes us into the realm of game theory. Now, one of the most popular games pits hawks against doves. Again, I'm sure many of you are familiar with this. The idea is that these two strategies compete for a valuable resource, which could be anything, food, a mate, whatever. And the idea of the game theory approach is that the payoff that you receive depends not just on your own strategy, but what the other player in the game is doing. So we don't need to go through the details, but you can see how whether or not you play hawk or dove and whether the other person plays hawk or dove affects the payoff you each receive. Now, this is potentially a very interesting area to bring into human metabolism. And there's a fantastic book which I encourage anyone who's interested in this to read, published by a friend of mine, a colleague in India, Milind Watve. It's called Doves, Diplomats and Diabetes. And Milind wanted to adapt the hawk-dove game to explore variability in human metabolism. So he renamed hawks and doves as soldiers and diplomats, but it's very much the same concept. And his argument that was hawks and doves don't just need to have behavioral strategies. Underpinning that, they need metabolic strategies as well. And he suggested that soldier hawks would benefit from high muscularity, and that should make them insulin sensitive so that they could divert glucose into the muscle tissue, and that would help their risk-taking and aggressive behavior. On the other hand, diplomat doves are not going to fight when they meet a hawk. They're going to try and be clever, and they use cognitive skills. That means they want to invest in the brain, and they should be insulin resistant so that they can divert energy away from the muscles towards the brain. And that also makes them risk avoidant. Now, I think this is a fantastic approach, and I really look forward to seeing it developed further. The idea that the metabolism we have may reflect our position in social games. But there are some limitations to this model. It doesn't say very much about development, and in particular, it doesn't really say that much about nutrition and where we obtain food from. So there's another game which is perhaps a little bit more relevant, and that's the producer-scrounger game. Now, an animal has a choice. It can either go out and find some food itself, or it can let others go and find the food and just try and steal it. And you often see this taking place with seagulls. In this case, you're outsourcing the costs of foraging to other individuals, and potentially in the same species. Now, this is another classic game, so what you should do depends on what others are doing. So on the bottom here, we have the number of scroungers going to the left and the number of producers going to the right, and you can see that the payoffs for each of the two strategies change, and then you get an evolutionary stable strategy with the optimum balance of producing and scrounging, either an optimum ratio of producers to scroungers, or the optimal amount of time that each animal should produce or scrounge. So here's a typical producer. It's a puffin from the Farne Islands, and you can see he's got a very nice beak full of sand eels, which he is just bringing home to his nest of offspring, so he can provide parental care. The trouble is that his fish are really visible. Even from a long way away, a human can tell whether a puffin has been successful getting fish or not. And as well as that, the puffin is a pretty dumpy bird with short wings. It's not able to fly very fast, and it's not very agile. So when the puffin gets back to the island, this is what happens. A number of nasty scroungers appear, and they don't attack the puffin. They're really trying to get the fish from its beak. And so the poor old puffin has to nest underground, and you see them flying in, and they literally just go straight down their burrow to land. Have a pretty tough time. Now, if individuals start to diverge towards being producers and scroungers, we might expect energy payoffs. So if producers are able to keep the food that they find, then that's called the finder's share, and they will end up with more energy than the scroungers, who will not be able to get much food from scrounging. But if the scroungers are very good at getting the energy from the producers, then they will end up with more energy. So we could see potentially life history differences emerging between these groups. Now, much of the book that I've just written has tried to explore the producer-scrounger game across a number of different modes of human subsistence, such as foraging and horticulture, through to industrial agriculture. It's not one constant game. It varies according to human behavior. One thing we can say is that farming inherently favors scrounging. If some humans go and group together fat, healthy animals and also plant lots of foods and fields, then some other humans may decide it's really convenient just to turn up and take them through aggression. So the archetypal scrounging would involve the producer producing some food and the scrounger just taking it from them, so that it's the food that passes from the producer to the scrounger. And you can literally see that in many forms of human society. This is a wonderful artifact which is in the British Museum just down the road from here. It's literally one street away. It's called the Standard of EHBEA, and it comes from Mesopotamia, 2600 BC. And it represents a very early feast. And in the top panel, you can see the elite, who are all seated facing the most prestigious person in the top left, and they seem to be holding some wine glass in their hand, and they're listening to some music played by the person with the harp on the right. So they're doing very well, they're enjoying a very nice meal. But in the middle and the lower panels, you can see all the people who are working very hard to prepare the feast. And that's what the artist wanted to show on this. All the people growing the crops, carrying the crops, looking after the stock animals, and so on. So that's a producer-scrounger society. Now, how can humans get some people to do all the work of producing food and then just take it without doing the work? And humans have actually found several different ways of doing this. There are ideological forms of control, defining the world as made up of different classes, and you have to do whatever it is that you're told is right for your class or caste. There are economic pressures, imposing debt on people and then forcing them to work to pay back their debt, or demanding that they pay taxes. And there's also overt physical violence. What we should expect is that if producers and scroungers routinely get different energy supplies, they should differ in their life history strategies. So we should expect producers to have a higher extrinsic mortality risk, a faster rate of aging, shorter lifespans, they'd be smaller in adult life, they'd have to produce more offspring to compensate for the higher rates of child mortality, and the offspring themselves will be smaller. So literally you're seeing a faster rate of aging predicted in the producers. And if we look at one specific trait, we see exactly that going on. So these are two populations from 19th century Europe showing growth through adolescence into adult life. And you can see that the working class or the labouring class have shorter height throughout this period, and by the time they get to adulthood, that difference persists. So here's a growth cost, if you like, of being a producer. And we also know that that's going to have intergenerational effects. So going back to the Brazil study, you can see that the wealthier families were able to invest more in the next generation and produce babies who were bigger at birth and had more weight gain, and of course that is good for their ability to resist the diseases of wear and tear. Now, one of the greatest ironies is that the farmers who produce all the food, and energy is, according to life history theory, the most valuable resource in evolution, they're actually disproportionately represented in the rates of child malnutrition worldwide. So this just tells you how strange the producer-scrounger game is in humans. Now, so far I've been talking about two groups, the producers and the scroungers, but we know that that's rather a simple model of society. But we can make it more complicated. We could think of a social ladder, so that some individuals are producing up for those higher in the hierarchy, and they're scrounging down on those lower in the hierarchy. So there's no reason why the producer-scrounger model can't be used to explore more complex types of society. Recently, scrounging has been reinvented, because now what happens is that through markets, producers produce food and they sell it to other producers who become consumers. And then scroungers only need to control the markets, and through that they can extract not food, but wealth. And that means that the producer-scrounger game now is very tightly associated with wealth inequality. We know that as diets change, it's not necessarily the healthiest foods that come into the market. These are data from pictures from Nepal, and you can see how two soft drink companies are trying to promote their not especially healthy products in this environment. We also know that although metabolism can respond to changes in diet, it can't do so at the optimum rate. And one thing we know, because of the fact that it's only plastic in early life, is that metabolic capacity can only change a little bit across generations, whereas metabolic load can change rapidly within the life course. Now, I showed you earlier that it's possible to coerce production, but it is actually possible to coerce consumption as well. There are many aspects of the ways in which we eat or consume products, such as cigarettes, that are beyond conscious control. And the manufacturers of products know very well that the content, the macronutrient content, or stimulants such as nicotine or caffeine, or the way they sell products can influence how much we use them. And we're also very susceptible to social norms, and that's been the case also for very long periods. So we can actually coerce people to over-consume. And if we look at the graph showing the inverse association between wealth and the prevalence of obesity, and we want to understand why we see higher rates of obesity in those most deprived, this is because it's not that poverty is restricting energy supply. Poverty is interacting with a predisposition to catch-up growth, and potentially targeting by companies to sell their products to this population. So we can think of the producer-scrounger game as something that pervades human nutrition. It can also vary, and so the game can also have elements of negotiation. I've really given you a very simple portrayal where the scroungers are bad and the producers are working hard and they're good, but it's a bit more complex than that. There can be a moral element to the game. Scroungers can invest some resources in trying to look after the producers. Indeed, if they don't, the society will eventually crash. But essentially the message is that how the producer-scrounger game plays out, if you like, the intensity of the game, determines the prevalence of the penalties, the rates of undernutrition and, in modern societies, obesity and chronic diseases. And if the rate of scrounging intensifies, then this is what we should expect. We should see those who are the victim of the scrounging should end up with less metabolic capacity, and they should also end up with more metabolic load. In other words, a fast track for chronic diseases. And that helps explain why chronic diseases are most prevalent in those from poorer social backgrounds. So I hope I've shown you the benefits of trying to bring these different approaches together and to really try to develop a multidisciplinary approach. And I just want to end with three conclusions. The first is that we're still saying that at the proximate level, physiology generates chronic disease risk. But what's interesting is that we have a better understanding of the life course etiology. Your risk of developing these diseases is shaped right from the moment of conception onwards. In fact, even across generations, because the ovum that forms each human was present in the mother when she was a fetus. So I was present in my mother when she was in utero in my grandmother. Very difficult to take that in. We know that low capacity, metabolic capacity in early life, it shapes the susceptibility to diseases, but it doesn't necessarily actually generate them. High metabolic load in later life is the key trigger, and so we still need to direct public health resources and efforts to helping adults lead a healthy lifestyle. Perhaps we could be a bit more skeptical about how much of this is individual responsibility and how much comes from broader level factors. The second key conclusion is that selection has favoured substantial plasticity in humans, and that refers both to early growth plasticity and also through the life course in sexual maturation, levels of body fat, and so on. And we always need to remember that what evolution has shaped us to have is the ability to maximize fitness and not the ability to maximize health. So many of these axes of flexibility are good for tolerating stochastic environments. They don't guarantee that we're going to have good health in the obesogenic niche of today, which is also compounded by profound social inequality. And thirdly, nutrition is a fundamental social scenario. And I think the producer-scrounger game is a very interesting way to look at human nutrition. Indeed, human hierarchy essentially emerges through nutrition, even if today markets play a key role in that. You can think of two different metabolic syndromes, one where the body doesn't get enough fuel and one where the body gets too much fuel and struggles to actually deal with it. And each of those syndromes strongly tracks social rank. And therefore, whatever we do at the individual level in trying to encourage people to adopt healthy lifestyles and provide medical treatment, I think that public health really does need to get to grips with the way that we organise society and consider that if we really want to prevent chronic diseases, we're going to have to engage with the producer-scrounger game. So thank you very much for listening, and since I forgot to say at the beginning, thank you so much to the organisers for inviting me and allowing me to make this presentation.
Thank you very much, Jonathan. We have 10 minutes for questions. Ron.
So a growing body of literature, many studies in the U.S. has been finding really quite dramatic widening of these socioeconomic differences in health, but particularly in mortality and life expectancy. If you look at it from a period or cross-sectional perspective, it's particularly in the last 20 years or so, something like that, 5 years. If you look at it in a lifetime perspective, it's the birth cohorts at the beginning of the 20th century, around 1910, had very little socioeconomic difference in longevity, and by the time you get to people born in 1940, 1950, it's greatly widened. And I wonder if you have any, it's a wonderful talk you gave, I wonder if you have any thoughts about this.
I do think that obesity is a risk factor that can expose other sources of risk that may not have been activated. So that we know around the world there's always substantial variability in birth weight. But without generating a large metabolic load, the signal of birth weight may not have much to say about chronic diseases. And you could see that in one of the graphs I showed earlier, that if you were an adult with normal BMI, birth weight was not predictive of later chronic diseases. Now that's just one example, but I think obesity in particular and dietary trends are actually exacerbating and interacting with some other risk factors, so that if you like, they're magnifying, amplifying some of the axes of risk. And I think also society is becoming more unequal at the economic level. So what I've been trying to show here is that economic life digs into your body and reaches your metabolism and does shape the rates of aging.
At the back, yeah. We do have microphones too. Could I also ask you to identify yourself before you ask your question?
Yeah, Thomas Löfner. I really loved your talk. Really loved your talk. Thank you very much. Just one question following up on the gentleman just asking the last question about the inequality. The tendency that I saw from your talk to fall into one of the two metabolic syndromes based on whether, if I'm focusing on humans, whether you would be a producer or a scrounger, so to say. Would you say that that implies that markets as efficiency allocators or as kind of ways of allocate resources are ineffective?
It's a very grand question. I mean, I think all we can say is if you look at people who've criticized consumer culture, markets don't necessarily sell you what you really need. They sell you or they provide what may sell well. And if you look back at the history of capitalism, the wonderful work of Sidney Mintz, who showed us that the sugar plantations in the Caribbean may have produced a major stimulus for factory capitalism in the West. Food and people's ability to consume more food was right there at the very start of capitalist approaches to both nutrition and also the emergence of markets, even if those were rather strange markets. And even now, the food industry is a massive component of global trade and global capitalism. And so you can see that if you were able to influence those markets, you can certainly change the rate of profit. So I don't think any nutritionist is unable to see that markets are part of our spectrum of malnutrition today. We can have different potential solutions, but I think the producer-scrounger game is now played out in markets. And this is part of the problem. And part of the idea of bringing in an evolutionary approach is to get away from some of the rather focused models of inequality in the past, which have become very political. And maybe using an evolutionary approach provides a broader template through which we can explore some of these issues.
Anna has a question.
Yes, thank you for your talk. It was brilliant. I'm Anna Rotker from Helsinki. This ties into the previous questions. Your conception of social rank, it seems you tied it quite much to the kind of standard definitions of social class. But one could also argue that social rank is not only, for instance, access to income or resources, but is tied to smaller social community social ranks. Things like, for instance, somebody here could have a high rank here, but really low income. Or you could also argue that the standard measures of social rank, especially in societies which are not very, which are meritocratic, tap into other individual genetic and epigenetic differences. So I'm sure you have been thinking about how to define social rank.
Yeah, I mean, social rank is very complex, and I mean, there are elements of social rank that may be more relevant to allostatic load and the stress response and how one's psychological state of being. I think the bits of rank, the aspects of rank that I focused on may be particularly relevant more to nutrition and your capacity to have agency. So one of the things that I'm most interested in is how much agency do producers have to negotiate with their scroungers, and to what extent do scroungers actually try to prevent the agency of producers. One of the things I argue in the book is that nutrition is a very effective medium for removing agency from people. And that may be one of the reasons why we have such a profound magnitude of malnutrition in our species at the moment.